Bismillahir Rahmanir Rahim. In the name of Allah, the Merciful, the Beneficent. The importance of knowledge is such that it was after Allah Ta'ala taught Adam alayhi salam the names of things that the angels were made to make sajda to him. Similarly, the opening verses, the first verses revealed to our Prophet Muhammad sallallahu alaihi wasallam praise Allah Ta'ala as the one who gave knowledge to mankind, and He gave us knowledge of the things that we did not know. So we make dua to Allah that the knowledge that we will learn in this lecture should be of benefit to the ummah, and we make the intention to serve the ummah with the knowledge that we have, and we make the intention that to do this for the sake of the love of Allah. This is lecture 8 of our course, Introduction to Statistics for Muslims. This lecture is about density estimators for the data. Density estimators are improvements on histograms which we have been studying in the previous lecture. In this slide we look at a very small data set to understand what histograms do, and also to understand the effect of changing the bin size. So if the bin size is very small, then every bin will contain only one point, and that is the picture in the first bin. The data itself is of Egyptian stock returns. This is the overall return on the stock market in Egypt for 7 years. So in the first year the return was 10%, in 2007 it was 52%, in 2008 there was an overall loss and the return was minus 56%, and so on. So if we make the bin size 1, which means that we go from 10% to 11% is one bin, 11% to 12% is one bin, then all of these returns are separated by more than 1 point, so each point gets caught in its own bin. And so if you look at the top diagram, then every return is pictured separately as a little bar, and that shows that there is 1 point in that bin. Most of the bins are empty, and there are 7 bins which have some things inside them, and each of these are the 7 points. So you can see that each return is pictured separately in the top. Now we make the bin size a little bit larger, and we make it 10 points. Then you will note that there are most of the points get their own bin. So if you look at the rectangles, they are all of size 1, which means that the bin has only 1 point in it. However, there are 2 points, the 10% in 2006 and the 12% in 2010. These two are combined together in one bin. So this creates a little bit more interesting picture, because you can see that there is a center in this graph. The center is around 10, 12, because these 2 points have now added to each other. They have, in one bin there are 2 points, so that bin becomes the central and the most important bin, and on that, in the tails, in the both ends, you have only 1 point. So the picture becomes a little bit more clear. Then when we make the bin size 50, which is a very large bin size, Then there are 2 bins. Most of the minus 49, yeah. So there is one point which is below minus 50, and that is one bin. So going from minus 100 to minus 50, there is 1 point, and then going from 0 to minus 50, there is 1 point, that's minus 49. So it turns out that the minus 49 and minus 56 get separated and put into different bins. And then going from 0 to 50, we have 1, 2, 3, 4 points. So 10, 12, 36 and 41, they all get put into one bin. And then there is 1.52%, which is even larger. So now we have a much nicer looking histogram, and the pattern is obvious. Most of the data is within the 0 to 50 range, and then there are some tails. This data is actually negatively skewed or left skewed. The tail on the negative side is large, the tail on the positive side is small. So as we increase the bin size, we get a better overall picture of the data, and as we decrease the bin size, then each point is pictured separately. There are 2 major defects in histograms which are handled by density functions. One of the defects is that the bin size and position is fixed in advance. It is not determined by the data. So I decide that we will make a category from 0 to 50 and one from 50 to 100. This decision is made without actually looking at the data. And the other thing is that the histogram, every point is represented by a rectangle, and also no matter where in the bin that point is, the same rectangle is chosen to represent that point. So the density functions avoid this problem because each data gets a bin which is centered at the data itself. So if the data is near the start of the bin, it gets a rectangle or some other shape which is centered around the data point rather than being fixed in advance. Also, we replace the rectangle by a smooth curve. So basically the idea of a histogram is that each point is replaced by a smooth curve which is centered on that point. This idea will become clearer as we illustrate it by several examples. So we start from the simplest case. Suppose there is 1 point at 0 only. So the histogram would be just one simple rectangle around it. Now instead of the rectangle, we look at the normal curve. What exactly is the normal curve? I won't give the formulas and the equations. I just give the picture of the normal curve. These are 3 normal curves. Any one of these 3 could be the density estimate, because there is one choice. Just like we in the histogram we choose the bin size, so in the density estimate we choose what is called the window size. For the normal distribution, the window size is represented by the standard deviation or SD, and the standard deviation or SD, if it is small, it means that the normal density is very concentrated. So the smallest window size here is 1/2, the SD is 1/2, and the blue curve is the narrowest, and it is most closely concentrated around the point. As we make the window size large, this is like making the bin size large, so the same point gets spread out over a larger area, and so the peak also comes down. So the red line, the red curve, is the density estimate, which has SD equals to 1, and the green curve has an even larger window size corresponding to a larger bin size with SD equals to 2. So this 1 point is now spread out over a large range going from -3 to +3. So just like when we increase the bin size, 1 point gets represented by a very large range of values. So in the density estimate also, as we change the window size, we can have a narrow window size. If we have a narrow window size, then each point has its own little curve. If we have a large window size, then the point gets spread out over a large area, and different points become close together and they merge. Again, we will see this more clearly in later. Now we go back to the Egyptian stock market data, and we make a histogram for, not a histogram, we make a density estimate for it. So basically we make a narrow window, so SD equals to 1. So then when SD is 1, then since most of the points are separated by more than a distance of 1, so each point gets its own normal curve. So as you can see, -56, -49, 36, 41, 52, they all have their separate curves. 36 and 41 are a little bit close, so instead of having completely separated curves, the two curves are joined a little. But the most interesting thing happens at 10 and 12. These are so close that their two separate bumps become combined, and the normal density adds together, so we get a little higher bump at this 1 point. So this is the density estimate for the Egyptian stock market data with a relatively narrow window. It looks pretty much like the histogram with a small bin size, except instead of having rectangles at each point, we have a little normal curve, which is a smooth curve around that point. However, two of the points have gotten a little bit merged together. Now we study the effects of increasing the window size on the same Egyptian stocks data. We go from SD is 10, which is the top left hand drawing. So if you look at the drawing, the pink curves is the sum of all of the individual normal curves. There are 7 different normal density curves. Each point gets its own curve, and the density estimate is the sum of all of those. If there is no overlap, then basically the sum will be just a sequence of bumps. But as you can see, when we have increased the window size, then there is a lot of overlap. The curves for different points, you see there are 2 negative points on the negative axis. We are looking at the first top left hand diagram, and there is a blue curve and a red curve. These are the 2 negative returns. They both add together, and then the pink curve, which goes up quite a bit, it looks like just a single curve. The 2 points have become merged together, and so we see that this density estimate is telling us that there is a peak at around -55 or so, or maybe even less, -55, let's say. So basically it's saying that when you look at the negative returns, they are centered around -55. On the right hand side, there are 2 bumps. Basically the 10 and the 12 are close together, and they are representing the first mode, and then the three positive returns, I think it was 36, 41 and 52, they have combined to create a third mode. So this density estimate is telling us that there are three different modes. On the negative side, there is a mode around minus 55. So if there are negative returns, then they are centered around minus 55. On the positive side, the 10 and the 12 is one mode, which is probably around 11. And then 36, 41 and 52 provide the third mode. So an interpretation of this first graph with the SD equals 10 is telling us that the stock market behaves in three different ways. Sometimes it's bad and negative. In those cases, the average negative return is around minus 55. Sometimes it's a little bit good, so average return is around 10-11%. Sometimes it's very good, in which case the return is around 45%. So this is the picture that is created by a density estimate which has a small window size, but not a very small window size. Now when we increase the window size to 20, we come to the bottom left hand side graph. When we increase the window size, then the differences, then points which are far apart now become closer together. If you look at the normal curve, you see that each point is getting a curve which is much more spread out than it was in the previous diagram. And so now if you look at the big picture, the pink, then there are two different modes. Now this is a bimodal diagram. In the previous picture it was trimodal. Now there are two modes. One is a negative mode at minus 55, which is more or less the same as the previous one, but now all of the positive returns have become merged together because of the higher window size, and we see that there is a mode around 30. When we increase the window size even further to 30, then all of the points become merged even closer together. Now the peak at the negative has disappeared. All of the points are and there is a because there are many more positive returns than negative ones, then they become dominant when you combine all of them with a large window. And so now there is a peak around 30, and there is a little bit of a shift near the minus 55, showing that there is some action over there, but now it's no longer separately a peak. And so this is now a unimodal diagram, and if you increase the window size even more, then even this little disturbance disappears and you get a very smooth picture with a single positive peak. So basically the goal of this exercise was to show how the density estimates change as you increase the window size. With the small window size you get a jagged picture. Each point is separately represented. As you increase the window size, the points start to merge together, and points which are close together just become combined, and as the window size increases, all of the points combine into one big picture. So in creating a data density, we have two choices. One is the choice of the window size, and the other is the choice of the kernel function. The kernel function is the function that we choose to replace the point. Now in this diagram, most of the commonly used kernel functions are displayed. The uniform kernel is the rectangular box, which is quite similar to the histogram. Each point gets replaced by a rectangle, but there is one difference with the histogram, and the one difference is that the rectangular box is centered at the point when you make a data density. As opposed to this, if you look at the histogram, then the bin size is fixed and no matter where the point is inside the bin, it gets the same rectangle. So all of the points within a bin get represented by the same rectangle, as opposed to this, when you're drawing a data density, even if you use the uniform kernel, every point gets a rectangle of its own which is centered at the point itself. Similarly, there are the triangular kernel, which you can see is green, the Gaussian kernel, which is another name for the normal. The Gaussian kernel here is quite flat. It's the smallest curve in this. No, actually, yes, that's right. The smallest curve, the lowest curve, the flat curve, which is under the rectangle, that's the Gaussian or the normal kernel. And the blue is the Epanechnikov. Epanechnikov is calculated to be the best kernel. But in practical applications, there is not much difference between the kernels as long as we use one of the smooth kernels. The rectangular kernel, which is uniform, or the triangular, which is sharp, these don't have very good properties, but otherwise if you use any smooth kernel, they all work in quite the same way. However, mathematically speaking, the Epanechnikov kernel has some optimality properties. We've already seen this once before, that as you vary the window size, the kernel becomes more concentrated around the point. Here the same effect that we saw for the normal density is demonstrated for the Epanechnikov kernel, and also for the rectangular kernel, which is like the histogram. As you can see in the top diagram, the small window size of h equals 1 corresponds to the blue curve, which is narrowly concentrated around the point. As you increase the window size to h equals 2, the curve becomes more spread out, it becomes less concentrated, and as you go to h equals 4, then it becomes even more spread out and even less peaked. So as we increase the window size, the point itself is spread out over a large area, and as we decrease the window size, it becomes, the curve which represents the point becomes very concentrated around the point. The same phenomena is visible when we look at the rectangular kernel. There are many ways in which these data densities are used. One of them is to classify the data into different groups. For example, if you have a bimodal density, this can represent a mixture of two populations, and you can use the two modes to differentiate between the two different populations. For example, in the Egyptian stocks data, the trimodal density could be interpreted as saying that there are three types of years: the bad years, in which you have about -50% return corresponding to the negative mode, and moderate years, in which you have about 10% returns corresponding to the middle mode, and good years, in which you have about plus 40% returns, that's corresponding to the highest mode. So things like this classification can be done using data densities. Now we will look at the World Bank classification of countries into low income, which is $1,000, 25 or less, lower middle, which goes from 1,000 to 4,000, upper middle is 4,000 to 12,000, and high income is 12,000 or more, 12,500 or more. This classification corresponds to incomes in 2011 using the gross national income per capita, and then using the Atlas method to convert incomes. The Atlas method actually is used to reduce the impact of exchange rate fluctuations, and it takes the average of exchange rates over a period of times and also makes an adjustment for inflation. It doesn't really matter to us exactly what this conversion method is. However, we note that this is not the same. In fact, it's quite different from purchasing power parity, and it has different types of problems and also different types of strengths. These are not of a concern to us in the present. All we want to do is to look at the data to see if it supports this distinction, this categorization. Can we find 4 modes corresponding to these 4 categories, or can we find cutoffs in the data? As we will see, the data doesn't actually support this division. Instead of looking at the GNI Atlas data, we look at the data set we have been looking at before, which is GDP per capita in PPP terms in 2010, and we look at the different window sizes just to give you a better idea of how the window size affects the density estimate. The first chart has a very small window, so more or less all of the points of data are getting their own normal density. So you can see that the graph is very jagged. Still, there are a lot of very poor countries, so near the 0 point there is a lot of combination. A lot of countries are merging together. In the upper part of the data, each country is coming out more or less separately, although there is a few combinations. So you get a very jagged picture. In the next picture, which is on the right hand side top, the SD, which is the window size, has been doubled from 100 to 200. As you can see, the picture has become smoother. More points are coming together, and still, although there is a lot of jaggedness, it is much less jagged than the previous picture, and points are being combined to make a smoother picture. When you go to 500, which is again more than double window size from the previous, then the picture becomes much more smooth, and now you can begin to see some divisions in the data. For example, there is a very sharp peak near 0, and then incomes go down, and then there is a second peak near around 14,000, and then it goes down to 0 at 20,000. Again at 30,000 it's going down to 0. At 40,000 it's going down to 0 again. So if we were to divide this, maybe the first division would be around 8,000, which is coming down after the first peak and before the second peak. So the second peak about 14,000. So maybe we divide we would say that the first division occurs around 8,000, the second around 20,000, and maybe that would be it. There would be 3 divisions. So that's what the data is telling us. If we look at the last chart, which is the smoothest one, the largest window size with SD 1000, the black lines here are the divisions that the World Bank is making, which is 1,000, 4,000 and 12,000. So these are the lines at 1,000, 4,000 and 12,000. 1,000 and 12,000 correspond to peaks, but the 4,000 is sort of in the middle. It's not really a nice way to divide the data. One doesn't really divide the data at the peaks, because on both sides of the peak you have similar incomes and similar countries. So this World Bank division, which is what we see in the black lines, is not really supported by the data, Therefore we conclude that it must be based on some other real world aspect and not just on the numbers. So we look at the same data with even higher window sizes. In the previous picture we had gone up to window size of SD 1000. Here we look at 2000 and 4000. As you keep increasing the window size, the curve becomes smoother and smoother, and you can see that in the 2000 SD win picture there is a natural bottom at 20,000. So if we wanted to divide this data into two parts, we would divide it into below 20,000 and above 20,000 on the basis of the data. However, the World Bank classification is not like that. It is going to about 12,000 as the largest, as the beginning of the rich category. If you go to 4,000, again the bottom is around 20,000 and the curve is a lot smoother and does seem to have two parts. This time this is more or less a unimodal density. Actually there is a small mode on the 30,000, so you could call this bimodal if you wanted to. Otherwise you could say this is a unimodal density which is right skewed, and there is a long tail on the right hand side. The main point here is that the density function does not support the World Bank cutoffs, and so we are forced to conclude that the cutoffs being made by the World Bank are not determined by the data and not determined by the numbers. They are determined by some real world factors which we don't know about. In this picture we want to show the relationship between the density estimate and the box plot. Here we have chosen this is the same data set, the GNP data set that we have been looking at in the past two slides. The window size has been set at 300. This is a relatively small window size which makes the graph fairly jagged, but it's not the smallest window size, as you have seen even smaller window sizes. So the graph, this is called an undersmoothed graph. As the window size is very small, the graph is very undersmooth. When the window size is very large, then you get a very smooth graph, and that's called oversmoothing. So there is supposed to be a perfect level of smoothing at which the graph is neither too smooth nor too jagged, but nobody knows exactly how to find that level. But anyway, the point here is to just show the relationship between the density estimate and the box plot. So we look at the box plot data. The minimum GNP per capita is 300. The first quartile occurs at 2500 roughly. So that's pictured by the vertical line. The second quartile is at 8000 and the third is at 22,400. If we draw these three lines, then just as in the earlier description, these three lines divide the histogram into 4 parts of equal volume. This is very important. The area under the blue curve is the same and is about 1/4 of the total area in each of these 4 sections. The first section is going up from 0 to 2500. You see that there is a very large peak there. So if you look at the area between that peak and the black line, and then you look at the second line goes from Q1 or the first quartile to Q2, which is the second quartile. Now the distance between Q1 and Q2 is large. It's about 5500. It's more than twice the distance in the first quartile, from 0 to the first quartile. But if you look at the area under the graph, it will be about the same, because this time now the density estimate is much lower. So basically the area under the estimate, area under the curve, measures the number of countries that belong in this region. So the box plot divides the data into 4 equal parts, and exactly the same thing is true here. The box plot divides the area under the blue curve into 4 equal parts. In all 4 parts, the parts are the length is becoming, the base is becoming larger, but the height is becoming smaller, and the area under the curve is equal in all 4 pieces technically. So if you look at those, then you can make the box plot on top as usual. The lower tail is very short. Then there's the part of the box going up from Q1 to Q2, which is from the first quartile to the median. Then the second half of the box goes up from the median to the third quartile, which is going from 8 to 22,000, which is very large, and the upper whisker is even larger. So you can see that the box is becoming stretched to the right, which is a sign of a very strong right skew in the data, which we have already seen earlier in many different ways. There is one outlier in this data set, which is Norway at 68,000. This is not included in the picture, because if we put it in the picture, that would distort the scale and make the rest of the picture harder to see. That's it. So we have seen that the data does not support the World Bank cutoffs. If we make cutoffs on the basis of the data density or of the box plot, we would not get to the same numbers as the World Bank did on the basis of the GNP per capita in purchasing power parity terms. So now our goal is to look at the data that the World Bank itself has used and see if maybe that makes a difference. So on this slide, we're looking at the GNI, the gross national income per capita, and now this has been measured using the Atlas method, which is the one that the World Bank uses. As we discussed earlier, the Atlas method is a way of stabilizing the exchange rate so that it doesn't depend on short-term fluctuations. So it takes the average exchange rate over a number of years and also adjusts for inflation rates. If you see that this chart lists the bottom 10 countries and the top 10 and the middle 10, they are ranked and they are sorted. These numbers are quite different from the purchasing power parity numbers. The minimum income was 300, but now here the minimum income is for Zaire 190 only. Purchasing power parity helps poor countries because the same basket of goods can be bought for smaller price in the poorer countries, and so when you adjust for this purchasing power, the poor countries become somewhat richer, because although the income is less, you can buy more with it. So here the minimum country is Zaire, I think, with 190, and it has rank 195. There are a total of 195 countries in this data set. Similarly, we have Thailand in the middle. All of these 3-digit codes are given in the World Bank data set, and they are given in the spreadsheets that you have been working with. CHN stands for China, and if you look at the top 5 countries, that's Sweden, Denmark, CHE, I don't know what that is, Luxembourg, Qatar and Norway. All of these are high income countries. Then basically you can see that there are only about 6 countries which have incomes above 50,000 in the whole data set of 195 countries. So these are upper outliers, and if we exclude those, it will make the scale of the graph sufficiently small that it will be possible to look more carefully at what is happening in the normal range of the countries. If we include these outliers, then the scale of the graph will become much larger, and the range 0 to 50,000 will be very compressed, and it will be much harder to see what is going on in that range of countries. In this slide we have a picture of the data density using a very small window size, so all of the data on the upper end is just pictured individually. Every data gets its own density, and there is no combination. On the lower end, the poor countries, they are so close to each other that even at a small window size they combine with each other, but you can see that there is a very jagged effect. The graph is very rough. We also calculate the box plot information. The minimum value Q0 is 190, the first quartile is 1295, the second quartile is 4440, the third is 12110, and the fourth is very far away at 88,870. So this is the maximum of the data. Now these numbers, Q1, Q2 and Q3, are fairly close to the World Bank cutoffs. So the World Bank cutoff, this is the exact GNI Atlas data they have used. The World Bank cutoff was 1000. Here this is around 1300, and the second cutoff was at 4000, and this is pretty close to that, and the third one is 12,000. So basically it seems that the World Bank started with these. They want to divide the countries into 4 groups of roughly equal size, and if that's what you want to do, then these numbers are a good place to start. And probably after looking at these numbers, then they made some subjective assessments by looking at the countries that are near the borderline and deciding which one should be classified as poor and which one should be classified as rich or richer. And so basically this seems like the source, or at least the beginning point, for deciding on the cutoffs for the rich and the poor countries. Now if we look at this, we are going to analyze the same data again by data densities. If you look at this, there are a number of problems with this graph. The scale is too large. It's going up to a maximum of around 90,000, and if we reduce the scale to 50,000, we make them, then it will be much clearer and easier to see the picture of what is happening for most of the countries. And at 50,000 we only eliminate about 5 or 6 countries, so we don't really lose much from the data set. The box plot data is telling us the same story. The third quartile is at 12,000 and the IQR is 10,000, so the maximum size of the upper whisker goes to 28,000, which is way below 50,000. So even at 50,000 we will have some countries which are outliers according to the box plot. We could put the box plot on this graph, but it would be difficult to see because the 190, the minimum, the box plot would be very compressed. The scale is 80,000, the box plot only goes up to about 28,000. So we will now reduce the scale and look at different ways of plotting the data density to understand more about how the data density helps us to understand the data. Both of these graphs are exactly the same as the one that we have already seen, but we are just reducing the maximum on the x-axis and not changing anything else. So the SD is 100 in all three of these graphs, the first one that we saw in the previous slide and the two that is here. 100 is a very small window size, so that means that this graph is under-smoothed. It is very jagged, it has a lot of sharp peaks. The top graph goes from 0 to 50,000 and eliminates 6 outliers. You can see that in this one a lot more detail is visible. The bottom graph only goes to about 16,000. So now we can see a lot more detail in the graph in the poor countries. The black lines are roughly the World Bank cutoffs, and as we have seen, they are also not too far away from the quartiles. So in fact these three lines can be used to construct the box plot in the bottom graph. And the bottom graph, it's roughly equal areas between the black lines, equal areas under the curve, roughly speaking, because actually the quartiles are a little bit different. The first quartile is at 1200, not exactly at 1000, but there is a rough correspondence between the quartiles and the World Bank cutoffs. So the main point of this is to show that when you change the scale of the graph, you can see a lot more detail. So when the x-axis is going from 0 to 16,000, the picture is much clearer and much easier to see, and when the picture is going from 0 to 80,000, then the curve in the range 0 to 16,000 is very compressed and very hard to see what it is trying to show us. We now look at the data density for this GNI Atlas 2011 data with different amounts of smoothing. So the window size is very small in the first graph, the top left hand corner. The SD is 200. This is still double what it was in the previous graph, which was only 100. So this is still a small window size, and you can see that the picture is quite jagged. We have reduced the scale so that the maximum is 50,000, and that makes the picture much clearer. And we can see from this graph that most of the countries are poor. In fact, there is a sort of a cutoff near 10,000, and after that, above 10,000, the countries are all more or less separated. So but below 10,000 we are getting a proper density graph, although it's still undersmoothed. There are a lot of jagged, sharp peaks in this area. So one natural cutoff here would be around 10,000 based on the histogram. In the second graph, which is on the right hand side top, we have increased the SD to 500. So at 500, the poor countries are now showing quite a smooth graph. That is because the distances between the poor countries are very small, so a small window size is enough to smooth the poor countries. As opposed to this, on the rich countries, the gaps between the incomes are very large, and so at this scale the rich countries are still not showing a smooth picture. So you can see that, you can say that at this level of smoothing, at this window size SD 500, the poor countries are getting over smoothed, but the rich countries are under smoothed. Smoothing depends on the size of the gaps between the incomes of the countries. If the gaps are small, then a small window size is enough, and if the gaps are large, then you need a large window size to smooth them. So in the next graph, which is bottom left hand side, the SD has been raised to 2000, which is 4 times the previous one of 500. This time the graph has become very smooth, and now even if we go to the scale of 80,000, there is not much loss of information, because the poor countries now are all showing one simple smooth picture. There is no jags, no peaks, no sharp corners, and this is what happens when you use a large window size. On the bigger countries, on the rich countries, you can see some patterns, but basically because most of the countries are on the poor side, so the pattern is not at all clear. So if you want to look at what's happening in the rich countries, then you have to change the axis, and this is what has been done in the fourth graph. The SD has been increased to even higher, 5,000, which is a suitable value for the rich countries and not very suitable for the poor countries. It is too large a window size for the small countries. All of them will fall into one bucket, more or less. But now what we have done here is that we have truncated, we have taken the poor countries out of the picture, because the poor countries are going up so high that this portion of the graph, the rich portion, we would not be able to see anything. They would all be very close to zero. So now what we have done is we have reduced the maximum on the vertical axis. At this maximum, you would not be able to see the poor countries because they go up much higher than 0.0015, and we have reduced the minimum on the x-axis to 25,000. So we are only looking at countries with incomes of 25,000 or more. Now by making these scale changes, the picture becomes much clearer, and you can see that there is a clear pattern of income among the rich countries. This is a bimodal graph, and there is one peak around 44,000 or so, and then there is another peak around 80,000 or so. So what we are seeing here, the graph is telling us that among the rich countries, again we have a bimodal distribution, and most of the countries are sort of moderately rich with incomes in the range of 40,000, but there are very few countries, there is a bump at the end, and there are a few countries which have a very high income around 80,000. These are the 5 or 6 outliers that we mentioned. Those 5 or 6 outliers are creating the second bump of the extremely rich countries. while the most of the countries are just moderately rich. So this kind of a pattern becomes clear when we change the scale on the axis. To be able to see it, we reduce the scale on the x-axis from 25,000 to 80,000, so as to focus on the rich countries, and then we also lowered the vertical maximum so that the picture would become clear. Otherwise, this would be, if we put in the poor countries, there are so many of them that the peaks on the poor countries are very large, and you would not be able to see this pattern on the rich countries. In the previous graphs, we have seen that the window size which is good for the poor countries is not so good for the rich countries, and vice versa. The problem is that the poor countries are clustered close to each other, so a relatively small window size is good for them. The rich countries are separated widely. The incomes, the gaps between two countries are large. So if we take a small window size which is suitable for the poor countries, we get a very jagged picture, very undersmooth graph for the rich countries. At the same time, if we take a window size which is suitable for the big countries, and that would be a big window size, then it oversmooths the poor countries. You lose the detail. You can't get a picture of what is happening properly in the poor countries because the window size is too large. Just like if you make a very large bin, then all of the countries go into the same bin, and so you can't see which country is where. So exactly in the same manner, when the window size is too large, then you can't see anything about the data separately. So one idea which is to use to fix this problem is called the variable window size, which means that at different places in the graph, the window size is chosen differently. One very simple way to do that is to look at the neighborhood of the point and look at, given any point, go 5 points below and 5 points above that point. So that is the local range. How much spreading there is at that point. So the local range is x of k plus 5, that's the 5 points above, minus x of k minus 5, that's 5 points below. So that's the range of values, that's the gap between the 5 above and 5 below. This gap will be very small in the poor countries, and this gap will be very large in the rich countries. So if we set the window size by taking SD equal to this range divided by 3, this will change the size of the window according to the point. If the point is for a poor country, then the window size will be small, and if it is for a rich country, the window size will be large. So if you look at this graph, this is based on this idea. The top graph, you can see it is smooth for the poor countries and also smooth for the rich countries. You can't see clearly the pattern of the rich and the poor countries separately. So in the bottom two graphs, we have just adjusted the scale so that you can see both pictures. This is so the bottom two graphs are exactly the same as the top graph, but they just focus on different portions of the graph by adjusting the axes. So the top graph goes from 0 to 90,000. This time there is no problem in that the poor countries are smooth and also the rich countries are smooth, because the window size is being adjusted according to the country. So we use different window sizes at different points. The top graph shows the picture of all of the countries. The middle graph is focusing on the rich countries, and it goes from 25,000 to 95,000, and the maximum size has been reduced, and you can see clearly the bimodal pattern that we have seen earlier. And the bottom graph focuses on the poor countries, so it goes from 0 to 20,000, and you can see that there is a very smooth graph which has a unimodal and has a mode at 4,000. Now we look at one more application of the data density estimation. We look at a data set that we have looked at once before. This is the infant mortality data set for the same WDI World Bank. The data set is displayed here in this slide. Actually we will be dealing only with the last year, the 2010 data. In 2010 the smallest infant mortality was in Iceland, which was at rank 1. It is the best mortality. And then in Sierra Leone it was the worst at 120.9, and that was at rank 158. So there is a total of 158 countries in this data, and they all have differing amounts of infant mortality. I have given here three groups: those which are very small, those which have some intermediate levels, and some which are very high infant mortality countries. Our goal will be to draw a data density for this 2010 data and then to see what we can learn from this graph. So here's a graph of the data density using a small window size SD equals 1. The light blue line is the standard kernel density estimator, which has fixed window size SD equals 1 at all points. The dark blue line is the variable window size, in which the window size become longer for the larger data points. As you can see, the dark blue line is smooth near the end. This is the effect of the high window size, which is automatically created at the end because the distance between the 5 above and 5 below points becomes larger and larger as we move towards the higher end countries, and the window size is controlled by this distance, and so the window size also becomes larger. So because the window size becomes larger, the right hand tail, the blue line is smooth while the light blue line is jagged. So this is the difference between fixed and variable window size, which you can see in the initial part of the graph. The two window sizes are matched, and so the dark blue and the light blue line are quite similar. But as we move towards the higher end, the variable window size of the dark blue line allows it to be smooth, while the fixed window size of the light blue line makes it jagged. What we see from this graph is that there are two peaks. It's sort of bimodal. Two peaks are both quite close to 0. One is very near 0, around 4 or 5 per thousand, and then there is another peak around 15, and that's also 14 or 15 deaths per thousand. And so after that there is a very long tail, that's all. But there are no modes in this tail, no significant modes. There are some small bumps, but they would not be considered as genuine modes of the data. Now in this slide we have the same picture as the previous one. I'm using the fixed window size here, and the window size has been chosen small, so we have a rough and jagged graph. We have under smoothing, and this picture isn't quite right. The dot plot has been put in a correct picture. The dot plot would come exactly under the curve, so the dots under the curve measure the number of countries that belong to that area. And as usual, the quartiles divide the data into 4 equal parts. So here the quartiles divide the data into 4 equal areas. The data density, the area under the data density, should be equal in all of the 4 portions of the graph. The 3 dark lines, the Q1, Q2 and Q3, divide the area under the graph into 4 equal regions, and these can be used as a basis for the box plot, which is also drawn above. And as you can see from the box plot, the median infant mortality is only 18.9 or 19, and there's a very large skew to the left. So this data is very much skewed to the left. The Sierra Leone infant mortality of 120 is an outlier, because after you add IQR of about 40 to the IQR is 40, so the 1.5 IQR is 60, and Q3 is 48. So when you add 1.5 IQR to Q3, you get 108, which is shown as 107, and this number is the largest length of the upper whisker, and nearly all of the countries fall in this region, having less than 107, except for Sierra Leone, which has 120. So this is the one outlier infant mortality. So basically the point of this graph is to show you the connection between the dot plot and the data density and the box plot. They all are displaying the same data but in different ways and with most statistical programs available in the market do not provide the variable window size estimator that we have been looking at. So the same kind of effect can be produced by using this program, by using some tricks which I will show in this slide. Basically, the top diagram is the automatic density estimate that is produced by the program for automatic density estimation, which is an Excel package. The top chart is for the full range from 0 to 120. The program automatically selects the right window size. As you can see that the program has made the density very smooth. Basically, the automatic programs do a lot of smoothing, and one of the problems with this automatic selection is that it has some density on the negative side. The program doesn't know that the infant mortality cannot be negative, and so it has produced an estimator which gives some possibility to the case where the infant mortalities are actually negative, although it's very small and not very important. So according to this automatic density estimate, there is a one very big peak near 0. This is around 5, and then there is a very large skew tail to the right, and this picture is over the entire range 0 to 120. As we have been discussing, the right window size for the small data set, for the small infant mortalities, is small, and the right window size for the large countries, the countries with large infant mortalities, is large. So one way to produce the kind of densities that we want is to just split up the data. and this is what has been done in the bottom two charts. The middle chart is for the low infant mortality, and it has a range from 0 and 32. So we take all the countries with infant mortalities between 0 and 32, and we feed this data to the program. It produces the automatic density estimate, which you can see. This density estimate is quite a bit different from what the top line shows, because in the top line there is just one peak in this region, but here it shows that there is something like bimodality in this data. There is one real peak near 4.5 and another almost peak near 12.5. So there are two different modes. These modes were picked out more clearly in the undersmoothed density that we looked at earlier. The bottom chart goes from 35 to 120 and shows a simple unimodal density with a peak at 51. This is the countries with high infant mortality. Once we eliminate the low countries, we take out all the countries with infant mortality below 35, then the program picks the right window size for the large countries. This window size is very small. This window size is very large compared to the one that was chosen for the small infant mortality countries. And because now this is adapted to the data, it produces the right picture. So these two pictures, separate pictures, one picture for the in the middle chart for the low infant mortality countries, and the second picture in the bottom for the high infant mortality countries. So we have now density estimates produced by automatic programs, not variable window size, but actually this is variable window size in the sense that one window size is being used for the low countries and another window size is being used for the high countries. So the point of this is that we can use automatic programs to create something like a variable window size by just splitting up the data into suitable ranges. And what we learned from this is that in the low infant mortality there are two possible peaks at 4.5 and 12.5, and in the high countries there is one peak at 51. Possibly there are three different types of technologies. Maybe the 4.5 countries, this is one group of countries where there is fairly advanced medical technique. We have intensive care, etc. The 12.5 is the second peak, where you can get to about this range by a second set of medical techniques, and the 51 is the peak for the rest of the countries where the medical technology is not so advanced. This is just a guess. One would have to investigate the real world causes of infant mortality to get more and more accurate information about this. Now we look more carefully at the same picture that was in the previous graph. We look at the low infant mortality data and we undersmooth it by setting SD equal to 0.3. There is one important point which I have not made before, and that is that there is general consensus that we should use undersmoothed pictures as opposed to oversmoothed. Yani if you have to make a choice between kernel size, choose a kernel size which leads to a rough picture, a small window size, rather than a large window size which makes a smooth picture. Smooth picture is more pretty to look at, but from the smooth picture you cannot get back to the undersmooth picture. While if you have an undersmooth picture like this, our minds are fairly good at eliminating the irregularities and imagining a smooth picture. So from the undersmooth picture you can get to the smooth picture even mentally, intuitively. We can understand what it would look like, but you cannot go the other way. So there is more information in the undersmooth picture and less in the smooth picture. So coming back to this picture, we have the orange and the blue curves. These are variable window size and fixed window size pictures. Notice that there is not that much difference, because once we have restricted the range between 0 and 30, so the size of the distances between the data is not that different. If we took the whole data set, there would be much more difference, because the gaps between the infant mortality in the high infant mortality countries are large, and the gaps in the low IM countries are low. But here all the countries have relatively small spacing between them. Still, you can see, if you look towards the end, that the orange line is a bit smoother than the blue line. Also, you can see that there are two peaks here. There is one peak at 4.5 and another one at 3. Now this is just likely to be an artifact. It's not a genuine phenomena. It's not that there are two types of country, one which has a infant mortality of 3 and one which has an infant mortality of 4. It's just that the data here is such that it is producing artificial mode, and if we smooth it a little, this mode will disappear. So basically in this data we see 3 modes. One is at 14, and one is at 4.5, and one is at 3.5. The 3.5 is an artificial mode, not genuine. So basically this data reconfirms the same idea that we had before, that there are two groups in the low infant mortality countries, one which have really low infant mortality of around 4.5 or so, and another group which has low infant mortality of 14 or so. Possibly there is some difference between these two types of countries. There might be two different types of medical technology, or the groups in which the infant mortality is 4.5 might have access to some special medical technology which is not available in the countries which have larger average around 15. So this more detailed examination of the low infant mortality tells us a little bit more about these data density pictures and what they can tell us. So what have we learned from this analysis of the infant mortality data? Well, one could argue, if you look at this data, that in 1990 Pakistan had infant mortality of 95, and now it's 60, or even better if you could go compare 1980. So then in 30 years our infant mortality has come down by 1/2, so Pakistan is doing well. Well, always in such comparisons one has to think about what is the benchmark, what are we comparing it to. If you make a comparison without mentioning what you are comparing with, this can frequently be misleading. So the issue is to compare how have other countries been doing over the same period of time. So if you look at this same data set, I've picked out countries which are comparable to Pakistan, and you can see that, for example, in Sri Lanka, which is the infant mortality is at 10.8. In Egypt it is at 19.1. In Bangladesh it is at 38. So if you compare to these countries, which are all similar structurally in that they're not very advanced countries, they don't have large amounts of money or lots of doctors in hospitals, you can see that Pakistan is not doing very well compared to countries to which it is quite similar. And in fact, our infant mortality is similar to that of Liberia, which is substantially less rich, and similarly Uganda. Even India has a substantially better infant mortality rate. So by looking at these countries, we can assess that Pakistan is not doing very well. But one very important thing to understand is that making this evaluation requires real world knowledge. I know enough about the world that I can pick out those countries to which we should be comparing Pakistan. I didn't put any countries from Europe in this comparison because the European countries have different structure, but this is something which if I only had the chart of numbers, I would not be able to tell. So again, we want to re-emphasize this lesson, that it is that numbers are never enough to reveal the truth about reality. Always the information that is being furnished by numbers must be supplemented by information about the real world in order to derive conclusions about the real world that we want to get from statistical analysis. So we conclude this lesson by some general remarks. Unlike what is widely believed in the West, that the numbers provide us with the final and the definite and the objective and the indisputable information about reality, the truth is that numbers provide only clues and hints and suggestions about what might be the case. One needs to, in order to learn about reality, and that is what knowledge is, learning the real names of things, we have to put together a lot of clues. Numbers are just one part of the knowledge that we need, and there are lots of other informations about the real world which are qualitative, which cannot be reduced to numbers. If we use a lot of clues and we put them together, we can sometimes learn something important and useful. What are the important and useful things to learn? One of the most important things is about the objects that exist in the real world, many of which are unobservable and unquantifiable, like the level of faith in a man's heart. This is a real thing. There is a force, there is a courage, there is trust, there is honesty. All of these things are real, but they're not measurable and they're not observable. So but they do have a lot of impact on the world. The West has ignored all of these invisible things, and as a result they have come up with a very distorted picture of reality. Now the numbers will provide us with some information about the real world, and this information will be used together with our other knowledge about the real world to put together what are the objects that exist and how they interact with each other. These are the causal chains. What affects what real object affects what other real object in what way. One has to look at mechanism. These things are ignored in conventional statistical analysis, and in the end, as the Quran says that we have been given very little knowledge, we must have humility. We are not able to actually get through to any knowledge of any kind unless by the help of Allah. So we end by a prayer to Allah that Allah Ta'ala accepts our struggle and striving for acquiring knowledge in order to serve Allah Himself and His causes. And if He accepts, Allah Ta'ala may grant us the ability to be of service to the Ummah and use this service to elevate our position in the Akhirah and forgive us our sins and make it possible for us to be of those who are saved from the hellfire on the day of Akhirah. Ameen.